All right, good afternoon, everyone. Thank you for joining this session this afternoon. So today I'm going to talk about service mesh, how we can secure APIs that are exposed via the microservices using the service mesh architecture. And I'm Sreena Achuthan, and I work as an information security officer at Capital One. And my focus areas are risk management, end-to-end access management, vulnerability management, and data protection. So I have a few housekeeping items here. I'm not going to go over that. All right, so the objectives for today. First, I'm going to talk about why we are talking about this subject today, why service mesh. We will look at what is service mesh, some of the components of service mesh, how does this technology work, and the role of service mesh in enhancing the security of microservices architecture. Then we will look at some popular service mesh products out there. And then finally, some best practices for implementing this service mesh technology. All right, so why service mesh? Microservices have gained popularity over the current times, with most of the modern websites that are currently built with the microservices architecture. Research shows that approximately 81% of the companies currently use the microservices architecture for building their application. The ones that are not there yet are also moving in that direction. It just takes time. And why are the companies using this architecture? Because it allows for faster deployment of services. However, this architecture uses a distributed pattern. So because it's a distributed system, it leaves a large attack surface area, leaving all these microservices vulnerable to threats. So how can we prevent these or minimize these threats on these microservices? And that is the subject of our talk today. And service mesh is what addresses these security concerns for these microservices. Service mesh provides a decoupled network infrastructure layer, which helps with secure traffic flow management, access policy enforcement, as well as telemetry data aggregation. And we will talk about these 3 points in detail later during the presentation, but that is what helps with decreasing the security concerns on the microservices architecture. So before we go deep dive into service mesh, let's look at what was before the microservices architecture, so we can get an understanding of why what was before what we have and why it didn't work, and why we are where we are now. So software journey started with monolith architecture, moving on to service-oriented architecture, and finally to microservices architecture, which we have today. Now, let's look at what is composed of what is a monolith architecture. In a monolith architecture, all components of application are tightly coupled together, and they function as one indivisible block. It typically consists of a client side, server side, and a database. It is developed as one single code, or all the codes are connected together. Because of that, it was simple to develop as well as simple to deploy. And it was easy to debug and test as well, since it was one single piece of code all connected together. However, when the monolith expanded, the complexity also increased. And now, since it was one single piece of code talking to each other, the changes became challenging, risky, and expensive to make. And it was hard to implement new technology, since we had to use the same languages that we started with, or the same platform that we started off the monolith with. Also, the monolith had a siloed implementation. It did not expose any APIs, or it did not have any interfaces or listeners. Because of that, if one monolith wanted to talk to another monolith, it could be done, but it was very hard and expensive, and developers had to spend a lot of time doing that implementation or connection. Also, all the components worked in one single thread. So if one component had to be scaled, it couldn't be done. We had to scale all the components across the board, which resulted in a lot of wasted resources. So the industry slowly moved on away from this architecture to something called the service-oriented architecture, or you will hear it as SAO-based architectures. Now let's look at what makes up this architecture. In the service-oriented architecture, the phrase called services became popular. Developers started creating services. One service provided one business capability, and this service had a very well-defined API. And since these services were separate services, it was language and platform independent. You could create the services in whichever language you wanted or whichever platform you wanted. And it had three parts: the services, the ESBs, and the service consumers. All the services talk to each other via the well-defined APIs, via this enterprise service bus, as well as the service consumers. So now what is a ESB? ESB is an enterprise service bus, which sits in the middle, and it acts as a centralized platform and takes care of all the items such as transport, routing, monitoring. All of those things were taken care by the enterprise service bus for all of the individual services. So some of the features of this architecture was that each of these services were reusable. Developers could pick and choose whichever service they want, and they could build that application. And also, since each of these services were developed independently, the software quality of these services were also very high. However, as I said, the enterprise service bus was the middle layer that helped with all the routing, messaging, and everything. So slowly it created a bottleneck. The ESB became very bulky, and it became very hard for companies to manage it. Moreover, the enterprise service bus platform was provided by big companies like IBM and Oracle, and they were very expensive for smaller companies to even get started. For larger companies, over time, it became very expensive to manage it. So all this increased overhead led to the demise of this architecture, and the industry started adopting the microservices architecture, which we have right now. So now, if we look at this microservice architecture, the microservice architecture, again, here brings in the concept of microservices. So it is a collection of several small microservices that are independently deployed and in specialized containers. Each microservice performs its very specific business capability or tasks that are owned by very small teams, sometimes called as feature teams. It will be one or two individuals who would be responsible for this microservice. And all these microservices could communicate to other microservices using very lightweight protocols such as REST over HTTP or HTTPS, which all of us are very familiar with those terms. This architecture had a lot of great features. It was scalable. The services could be scaled independently. It was resilient. A failure in one service did not bring the entire system down. It was flexible. You could independently update services, making it very easy to do rapid deployment. It was tech agnostic, as I said. This teams could choose whichever platform or language that they wanted for this architecture. However, as the number of services increased, the complexity also increased. Also, because of the distributed nature of this architecture, it became difficult to ensure security and privacy. So let's look at those 2 points in a little bit detail. Right. So what are the challenges of the microservices architecture? On the right-hand side, I have the microservices architecture of Uber. So as you can see, all these green dots here represent the microservices that are deployed in the Uber microservices architecture. So as the company size increases or the architecture becomes larger, the number of microservices deployed in the organization also becomes larger. So these are like more than thousands of microservices that are deployed in the Uber architecture. So for such a distributed architecture to function very effectively, communication is the glue. Communication is the glue that holds this architecture together. So what can we do to make sure that this communication is effective and all the microservices are able to communicate? Some of the things that we need to make sure are service discovery. Each of these microservices will need to know which services are available so that they can talk to them and make sure that they are able to get the transaction completed. Also, we should have provision to make sure that if one service fails, it did not bring the entire system down or the network down, or there's no network lagging, right? So we need to implement circuit breaking, how many retries we should do, or also we should make sure that we have educate timeout configuration patterns set for this, for each of these microservices. Then since there are so many microservices in this distributed pattern, we want to make sure that if there is any abnormalities or there is attack around the environment, we need to be able to know that. So observability and monitoring becomes a key feature for this architecture. We need to be able to look from the top and see where the problem is and help and figure out the issues and resolve it. Also, some of these microservices may have card data or highly sensitive human data, and we need to make sure that the services that are not allowed to talk to these microservices are not talking to this. So we need to make sure each service has proper authentication and authorization mechanisms. So here I have an sample online store built on a microservices architecture. All the green boxes here represent the various microservices that are necessary for this online store to function. So let's take, for example, here the order management microservice. This is one of the microservices in that online store. For this, the developer who is building this order management microservice first need to write the code for the business logic for that order management function. And so it might be 10 lines of code or 20 lines of code that the developer is writing, right? And then this order management microservice need to talk to the payment microservice so that can complete the transaction in the event of an order. So the order management developer would need to write the communication logic to be able to talk to the payment microservice. And then the payment service has sensitive data. So the order management developer would now need to write the security logic to be able to authenticate to the payment microservice. Now, the payment microservice can fail at any time, and the order management microservice, if it continues to call the payment and it is not responding, it needs to know how many tries it should do before it says, okay, I'm quitting and I'm doing something else. So the order management developer needs to write the retry logic. And then the order management microservice itself can fail at any time. So if that happens, the order management microservice team need to know when it is failing and take adequate steps to bring it up. So it should also have the monitoring logic. So all of this logic on top of the business logic, the order management microservice developer would have to write all the extra logic. Also, let's assume that the search microservice over here is only exposing the TCP protocol, right? So then in that case, the order management developer will need to learn how to do a protocol conversion. So that's an extra task on him. So imagine that all of this logic that we are seeing here has to be duplicated across the microservices here. And depending on which language each of them is written, it has to be written in the same logic, has to be duplicated and written in the other languages or in the other platforms that each of these microservices are built. So how can we help the developer here? He's spending a lot of time on writing all this extra code when he should only be focusing on business logic and make his code much better and better, right? Also, with all this extra code added to a microservice, this is not micro anymore. It is becoming bulky. So, but we need to make the microservice really micro and nimble. So what is the solution here? That is where service mesh comes into picture. The solution is having a service mesh deployed on your environment. So now, what is a service mesh? Service mesh is a dedicated infrastructure layer that is built on top of a containerized application just for the purpose of the other extra logic. right? So it decouples the service logic from network concerns and provides several features such as security features, observability features, reliability features, and traffic management features. And this pictorial representation here, you can see that this is without service mesh. All in the microservice, you have all the logic written in one microservice. But with service mesh implementation, you're taking out all of this, and the service mesh handles all of this, while the microservice is only responsible for the business logic here. So what are the components of the service mesh? Service mesh consists of two major components that we need to deploy into our environment. These are the data plane and the control plane. The data plane consists of network proxies that are deployed alongside each of the microservice. And this data plane is responsible for managing the traffic forwarding, routing service calls, applying the rules of authentication authorization, implementing rate limiting, handling service discovery and logging, and implementing logging and tracing. Whereas the control plane sits on top and controls the behavior of these proxies that are deployed in the data plane and provides the APIs for all these network proxies. All the proxies in the data plane will need to register themselves in the control plane so that they can get the configuration details from the control plane. The control plane acts as the coordinator for the traffic forwarding across the entire microservices architecture network. Here is the pictorial representation for this. We can see that the control plane sits on the top and provides a lot of features where and the data plane sits on the bottom, and each of these microservices will have a proxy deployed alongside it, which talks to each other as well as the control plane and manages all and coordinates all the traffic flow and communication. Okay, now how does service mesh work? It is when you deploy service mesh in your environment, what happens is whenever a container is deployed, a proxy is deployed alongside each of the microservice. So each microservice is equipped with a sidecar proxy, which is a separate container or process that runs alongside each of the microservice. And this proxy is the one that intercepts and manages traffic to enable all the features that we said earlier are essential for the successful communication between the microservices, such as service discovery, load balancing, circuit breaking, encryption, authentication, and much more. These sidecar proxies constantly communicate with the control plane and has updated information on what are the policies that are set forth by the control plane. And whenever the proxies have copies of the policies on the control plane, and they use that to guide how it needs to communicate with the other proxies. So here I have a sample configuration file. There are two kinds of configuration files. One is this is the example of a deployment kind, and there is also another one called the service kind. In this deployment kind file, you can see that when the microservice is deployed in the environment, only the microservice is deployed. There is no proxy. So in this case here, the microservice is responsible for all the routing, all the logic. Whereas in here, when the service mesh is deployed with the mesh, when the container is deployed, you will have the microservice, and then along with it, an envoy proxy is also deployed alongside it. In this case, the microservice here is only responsible for the business logic, whereas here the envoy proxy will take care of the rest of the things for this microservice. So I talked about, we just looked over the deployment kind configuration file. There are two kinds of configuration file, the deployment kind and the service kind. This deployment kind is used for scaling and managing and bringing up the pods. This deployment kind ensures that the specified number of pods are running, and this is specifically used for application deployments and updates. Whereas the service kind configuration file, this is used for network connectivity between the pods, and it acts as a stable endpoint between the pods and the external clients. This service kind configuration file is used for accessing the application. Here on the next slide, I have the YAML configuration service kind file with microservice and with mesh and without mesh. Here it is without mesh. So you can see the port 80 is exposed, and the microservices communicate directly to the all of the ports in the microservice will be open, and the microservice talking to the microservice will communicate directly with each other. Whereas in here, all the ports for the microservices are blocked. Only the envoy proxy, the proxy has access to the internal ports. The ports of the envoy proxy will be open to the outside world, and proxy manages how it needs to, which service in the microservice it needs to communicate. So it is very well protected by the envoy proxy. So how does service mesh enhance security? In the earlier lecture, you might have heard about the term zero trust architecture. So, and if you're working in a regulated environment, this is something that you might have always heard, zero trust architecture. So implementing a service mesh in your environment makes sure that you can enable zero trust architecture. So what is zero trust architecture? Zero trust architecture is an approach to cybersecurity where we never trust. We always need to verify. Every digital transaction will have to be continuously verified. And since we never trust any of the digital transactions, so we keep on continuously validating at every step. So implementing a service mesh in your environment helps with zero trust architecture by delivering IT-based service-to-service access and communication. These are the features that are provided by service mesh, which helps with zero trust architecture. The service mesh provides secret and certificate management. It enables observability with audits and logging, and it also helps divide the network into smaller segments by limiting the scope of security breach. So these are all the principles that are essential to build a zero trust architecture, which service mesh provides, and you can make sure that you have a zero trust architecture with service mesh implemented in your microservices architecture. Okay, so let's deep dive and look into how service mesh helps with encryption. So this control plane in the service mesh provides a feature called certificate management. This certificate management feature in the mesh automates the management of certificates that are used for MTLS certification. This certificate management feature can be used to automatically rotate, renew, revoke certificates as and when needed. And this acts as a CA, certificate authority. And these certificates are passed on to the proxies. And these proxies use these certificates when it communicates with the other proxies. So every communication that is happening between the proxy are all encrypted and authenticated communication. So if there is an attacker in the environment, or if there is no chance of eavesdropping of sensitive data, because every communication is using the MTLS and encrypted and going as encrypted traffic. So now let's see how it helps with the authentication and authorization. So again, the control plane provides a feature for security authentication and authorization using the principles of RBAC and ABAC. So you can choose which one you want. If your organization is using role-based access control, you can set that up on your control plane. Or if we are using attribute-based access control, that is something that you can set up here. Whichever policy is set, that is what the control plane will communicate to the proxies, and every proxy has the feature to validate JOT tokens. And for every communication that is passing from proxy to proxy, the JOT tokens are validated, and that's how the service mesh ensures that the security of the whole service mesh is maintained. Now let's look at how service mesh helps with rate limiting. Rate limiting is a great feature that helps us enforce the limits on rate of requests that are sent to API-based service. So rate limiting helps with a lot of things. It protects us from DDoS attacks, brute force attacks, API abuse attacks, and also any attacks that rely on excessive traffic or resource consumption. So with the traffic management feature provided by service mesh, you can set global rate limiting as well as local rate limiting. So if you set global rate limiting, you can set the rate limiting for the entire mesh. Or if that is not something that you want to do, you can even set up local rate limiting, by which you control, you are saying that only this service has rate limiting, this service doesn't need rate limiting. So you can be very specific on which services would need the rate limiting or not. And again, this is a great feature that helps the architecture from a lot of attacks that are very frequent. Okay, network segmentation. This is another feature that's provided by Service Mesh. The Service Mesh has provides traffic management feature, and this traffic management controls how the network flows between the services across the entire mesh. The traffic management feature can provide with segmenting networking via several routing policies. Some of the routing policies that are provided with this service mesh are intelligent routing, load balancing routing, circuit breaking or retrying based routing, or traffic splitting routing. These can be used depending on what your need is. In the traffic splitting based routing is a special is a very great way of routing or splitting the traffic based on routing. In this routing methodology, say that if you suspect that there's an attacker in the network, you can split the traffic and isolate the network there and contain the attack in that area. So what happens is that you can prevent attacker lateral movement by using this routing, using this traffic splitting based routing methodology. So these are all options that are available in the traffic management feature of the service mesh. And you can, it's not, there is no restriction on which one you can choose. You can mix and match or choose whichever works for your environment. Now let's look at how service mesh helps with observability and monitoring. Like I said, the control plane again here provides a feature for telemetry, and the control plane has visibility across the entire network. It's talking to proxies all the time. It's constantly communicating to the proxies throughout. So it has information on all the proxies. So because it has information on all the proxies, it helps with logging, metrics, and tracing. So the control plane telemetry feature can let you bring in all the logs from the different proxies and dump it in some tools like Grafana or Prometheus or any of those tools, and you can analyze the behavior there. Also, the telemetry feature helps you set alarms if there are abnormalities in the environment. You can set alarms and then act on it if there is something that's happening in the environment that is not desired. Also, if there are issues in the environment, since it has visibility over the entire network, it can provide you visualized dependency identification so that you can identify the root cause immediately, which will help in your troubleshooting. So that's another great feature that is provided by the service mesh. So now, what are some of the popular service mesh out there in the industry? There are tons and tons of service mesh services out there in the market, but here I am presenting three major ones or three popular ones: Consul Connect, Linkerd, and Istio. These are all open source products. And if your Consul Connect is from HashiCorp, so if your organization is using HashiCorp products already, then this is a great way to go. Because it integrates very well with HashiCorp products. Linkerd is from Buoyant, and Istio is from Google. All of this follows the sidecar pattern that I went through earlier. The Consul Connect and Istio uses Envoy as the sidecar proxy, while Linkerd uses a very ultra light micro proxy called Linkerd 2 that's built on Rust language. Again, there are subtle differences between these three popular service mesh. Consul Connect, it supports multi-cloud and hybrid environments, whereas Linkerd, it's very easy to manage. So if you want to build something very quickly, then that is the way to go. Whereas Istio is maybe one of the most popular because it is feature rich. It has a lot of features. You will get all the bells and whistles with Istio. But as the features increases, the complexity also increases. So it's a little bit hard to manage and configure Istio. But if you want a feature rich service mesh, that would be the way to go. But it really depends on what your organization's needs are to pick and choose whichever one you want. Okay, so you can have all the tools and gadgets in the world, but if you do not set them up properly, or then it's of no use. So that's why I'm talking about some of the best practices that you have to remember while implementing service mesh in your environment. First, you can set up service mesh, but you can turn off MTLS. So you need to make sure when you're implementing service mesh, you need to make sure you're securing your communication using the MTLS feature to prevent man-in-the-middle attack. You should implement access control such as RBAC to prevent unauthorized access. That's another feature. So you have to make sure that you set that on. Use security configurations to enable authentication and authorization for the service mesh components itself. Then implement rate limiting. These are all great features. But if you do not implement it, then it's of no use. So make sure that you implement rate limiting, circuit breaking, and connection limits on service mesh to mitigate DOS attacks. Also, monitor mesh activity to track behavior and respond to threats in a timely manner. If you get alarm and you do not respond, you're just not acting on it, then it's as good as not setting it up. Then use network segmentation to isolate services. It provides a lot of different options to segment network. Use the one that works for you. The traffic splitting one may be a best solution here to isolate services. Then, as I said, the service mesh has information of your entire network. So it has logs about the entire log. So that's a very, and it also has configuration data about your entire network. So it is very important that we make sure that we are encrypting this data at rest. So if attackers get that data, then your entire network is compromised. So we need to make sure that we use encryption at rest to protect the service mesh logs and configurable data. And finally, the crown jewel, the control plane. We need to limit exposure of the crown of our crown jewel, the control plane, by placing it in a separate namespace. So that brings us to the end of my presentation, but I just want to leave with a few snippets that you may want to go back and research. There are several companies that has gone through this journey. Netflix was one of the companies that adopted microservices early on, and they went through their journey and they have adopted microservice mesh. So you can read up about their journey in the internet. It's a very fascinating journey. Another company that has gone through this journey is Airbnb. They also have the microservices architecture, and they tried to mimic the service mesh pattern using different tools and technologies, but finally they have also passed the canyon and implemented service mesh in their architecture. So these are some amazing stories that you can read up on the internet. So that brings me to the end of my presentation, and I can take any questions.